Hello class. Today we're going to continue our discussion of functions. This time we're going to look at what's called exponential functions. And it's a pretty lengthy assignment, 23 problems. And we've already said what a function is. That was several weeks ago. A rule that assigns to each x value exactly one y value. With exponential functions, we're going to have variables in the exponent. That's the first time we will have seen that. And so the first thing we need to do is review what are all of our exponent rules. So I'm going to start off by stating some rules. And the first exponent rule we're going to have. How funny. No, that one.
This one?
Yeah.
There
okay.
it is. Okay.
So our first rule is the definition of a zero exponent. Anything to the zero power is defined to be 1, except for 0 to the 0 power. So anything to the 0 power is 1. I'm using an A. If you wanted to, it could be stated, we're going to be using lowercase b's a lot. B for base. When we have exponents, the little thing is the exponent, the big thing is the base. So we could say b to the 0 power is 1. I'm not really sure how Pearson has it written as a rule. B, you think? Let's do number 1. Problem 1.
Got to be the easiest problem this semester.
I think okay. Negative 26 to the 0 power. It says evaluate negative 26 to the 0 power. Well, our first rule of exponents, anything to the 0 power is 1. So this 0 applies, that 0 exponent is applying to all of the negative 26. Anything to the 0 power is 1. Just not a lot of writing to get that answer there. Tim, why don't you pull up that calculator and just punch in. Sometimes students don't believe it unless they see it on a calculator.
Negative 26 raised to the 0 power. Sure enough.
Okay. Now, we have two definitions of negative exponents, and
based on whether the base of the exponent is a fraction or not.
I think I'll use a B. B to the negative n. If you have a number that's not a fraction raised to a negative power, that's defined to be a negative exponent is 1 over b to the positive power.
A negative exponent means the reciprocal of the base raised to whatever the power n is. And the reciprocal of b is 1 over b. Suppose that base were a fraction already.
There's another way of stating that definition. A negative exponent, when you have a fraction, a over b to the negative n. Here, a negative exponent, if it's a fraction, to simplify it, I guess I'll just do this. You flip the fraction. So
the reciprocal of a over b is b over a. The negative exponent means the reciprocal of the base, and then you use the positive exponent as the power.
So problem 2 through
number 2.
1 over 9 to the negative 2 power. 1 over 9 to a negative 2 power. Here we have a fraction. Wait, a fraction raised to a negative power. So that means we're looking at this rule. To raise a fraction to a negative power, you flip the fraction. If I flip 9 over 1, if I flip 1 over 9, I'd get 9 over 1, which I don't need to write as 9 over 1. I can just write it as 9. 9 squared is what? 81. There it is. So 1 over 9 to the negative 2 power is just another way of writing 9 squared, which is 81. What about number 3?
Wait, I gotta check here.
Oh, that's right. Okay.
This one won't be quite as clean as the previous one.
2 over 5 to a negative 2 power. Well, this is another fraction raised to a negative power. So what my brother meant when he said it's not going to be quite so clean, when you flip the 2 over 5, we're going to have a fraction, 5 over 2. Whereas when we flip 1 over 9, we just got the integer 9. So, but it's still not hard. Y'all can do that. 5 over 2 squared. 5 squared is? 25. 2 squared is?
4.
Good. So 25 over 4. 25 over 4. What about problem number 4? Oh, rewrite using a positive exponent. Okay. A to the negative 3rd. We want to write that with a positive exponent. Well, this isn't a fraction to a negative power. It's just a non-fraction. That's this rule right here. A to the negative 3rd. If you have just an integer to a negative power, to get rid of that negative, it's 1 over. So this red negative becomes the red 1 over. And what am I going to put in the bottom here? A cubed. Very good. So a to the negative 3rd is another way of writing 1 over a cubed.
So 1 over a cubed. Now we're going to go in the opposite direction.
I think I mentioned before, in algebra you always do it one way, then you do it in reverse. So there's 1 over 7 to the 9th. I'm going to look at the rule that involves the 1 over.
Okay, wait. 1 over 7.
I should have written the problem down. 1 over 7 to the 9th. They want us to write it with a negative exponent. In other words, they want us to write it without the 1 over. I'm going to write it without the 1 over. So looking at this rule in reverse, 1 over 7 to the 9th is the same thing as 7. What am I going to write as the exponent? Negative 9. Now see how I'm using that rule in reverse. 1 over b to the n is b to the negative n. I'm reading it in reverse like that. Okay?
So 7 to the negative 9.
Let's see what number 6 is.
Same instructions.
Oh, is that a p to the 9th?
That's a p.
1 over p to the 9th. Well, how do I write it with a negative exponent? In other words, I'm getting rid of the 1 over. To get rid of the 1 over, what am I going to do to that 9? Negative. That's when you look at it from from right to left, this rule here I'm pointing at, it's saying if you have a 1 over, to get rid of it, make the exponent negative. Okay? So p to the negative 9. Okay. Now, so we've looked at the definition of a zero exponent. There's not much to it. Anything to if there's a zero exponent, and whatever's being raised to the 0 power, that's a 1. Then we looked at the rules for negative exponents. Now, I want to state some rules that we had stated.
I remember it popped up with cube root equations.
Yeah, very early on, the first 2 weeks of the semester. It's a fractional exponent. A 1/2 exponent, we said, meant square root. Okay? You know what? Let me do this. Okay. A 1/2 exponent is a square root. A 1/3 exponent, I even had a problem with the 1/3 exponent on the midterm test.
Mm-hmm.
A cube root. A 1/4 exponent is a 4th root. Whatever this bottom number in the exponent is, that's the root. And as we mentioned way back, at first glance you might say, well, wait, you don't put the square there. Yeah, but you sure say it. A 1/2 is a square root. We don't write it there, but it's assumed to be there. A 1/3 exponent, a cube root. In general, a 1/n exponent is an nth root.
That number outside the radical is called the index. Whatever the index is, that's the denominator of the fractional exponent.
Since I've written all of this right here, I'm going to do problems 7 and 8 right here, so I can be looking at those. Problem 7 says,
Rewrite without rational exponents.
so that x, I don't really like the way the formatting looks there, the way they write the 1/9 vertically. I'd like to write it like that. Oh, you don't see it. So what it wants us to do is to rewrite x to the 1/9 without this fractional exponent, without the rational exponent. That means you need to write it with a radical symbol. So x to the 1/9, what symbol will I use to replace this 1/9 exponent?
A ninth root.
It's a 9th root. I draw the little radical symbol and put a 9 right there. X to the 1/9 is the same thing as the 9th root of x.
So we have to use our radical hot button. Don't use this one. This is the square root button. We need to use the nth root hot button. And notice it's flashing. What do I put up there as the index? That's the 9. And then underneath I type the x. Here's another one.
Number 8. Number 8. Rewrite without rational exponents and simplify if possible. Since there's not a variable, it's just numbers. That's why they're saying maybe you can simplify. 16 to the 1/4 power. I'll try to write it the way they do with the horizontal fraction bar. That red 1/4 fraction is the same thing as this red this red 1/4 fraction is the same thing as this red 4th root symbol. So let me put the radical symbol and a little 4 there. And now this one, it says simplify. What is it asking for? It says the 4th root of 16. Is there a number that we could multiply together 4 times that would get 16? Okay. Here's what you're wondering. What number raised to the 4th power will give us 16? Do we expect it to be a big number or a small number?
Small.
Better be pretty small, right? 1 doesn't do it. 1 times 1 times 1 times 1 is just a 1. So let's go to the next number, 2. If I multiplied out 4 2's, am I going to get 16? Yeah. Multiplying 4 2's, isn't that like multiplying 4 times 4? So what's the answer that we're going to punch into the box on this one? 16 to the 1/4 is the same thing as the 4th root of 16, which is 2. Just 2. Okay. What number can you multiply to the 4th power or raise to the 4th power and get 16? Just a 2.
Any questions in our logic there? Okay. Suppose the exponent isn't a 1.
Yep. Oh, I'll do these, and then you can take over. Right.
Suppose that exponent, the fractional exponent, has a numerator other than 1. That's a natural question.
Here's our rule. I'm now going to state how you simplify a fractional exponent if the top number isn't just a 1. Okay, 1 over 2, 1 over 3, 1 over 4. Here it is. B to the A over N power. Let me see. Is my greening showing today?
It looks black.
It looks black? Okay, well.
Actually, when you watch the video,
Yeah,
you can see
on the video it doesn't look black. Okay. In general, if you have an exponent, a fractional exponent, the bottom number we've already said is the root. Like the square root or cube root or 4th root. The bottom number is the root. The top number is the power. Wow, this looks horrible. I should have written it without the slanted fraction bar. I should have done it the way Pearson does it. B to the A over N power The bottom number is the root. The top number is the power. So there's two ways to write this symbolically rather than in words like I did here. You can go nth root of b, then raise it to the a power, or you could do the power and then the root. Usually, if you're using numbers here, it's easier to do the root and then the power so you don't get such large numbers. So you could have raised to the power and then take the root. And I think that's what the next problem is. Let's see.
I think this is the format I prefer.
Yeah.
Oh, okay. Let me see.
Do the root, then the power.
Number
9. Ooh.
Okay. This is one where you definitely want to do the root first and then the power.
256 to the 3 over 4 power. Okay, 256 raised to the 3 over 4 power. Here's my thoughts. I could start off cubing 256 first and then look at the power. The root. But wow, that's going to get you a huge number. The smart thing to do is to find the fourth root of 256 and then cube it. Okay. You don't want to cube first. 256 times 256 times 256, that's going to give me something really large.
So you're asking yourself, what number to the fourth power will give you 256? Well, we know it's not 2 to the fourth. We saw that was 16 earlier.
What about 3 to the fourth?
3 to the fourth? You think 3 to the fourth is going to give us 256?
No,
it's giving us 81.
Because that's the same thing as 9 times 9.
That's right.
What about multiplying 4? 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. So the fourth root of 256 is a 4. Do y'all see why I'm writing a 4 there? Where it's coming from. I'm doing just this fourth root. Now don't say 12. What's 4 cubed? 4 times 4 times 4. 4 times 4 is 16. 16 times 4, 64. Could you punch that into your calculator? Okay. So 4 cubed is 64. So 256 to the 3 over 4 power is 64. Any questions how I'm doing that? I did the root, the fourth root first. That's what I was doing right here in the parentheses. It was a 4. And then I cube. I do the root, then the power. Number 10.
16 to the
You want to do it?
Oh, no.
Okay. Okay, I'm going to turn off my microphone.
Yeah.
There, you do it. Okay, 16 to the 5/2 power. Oh, that might have been a better first. I was thinking the same thing. That's what I was going to say when you asked me, did I want to do it? I was like, well, I was going to say, in words, could you say what we're going to be doing here? We're going to take what root? What sort of a root are we going to have for this number 16?
a square root. The denominator there is a 2, so we're going to have a square root. We have, what have we got under the radical? The 16 is under the radical. And we're going to have to raise that all to the power 5. Once again, I hope you see why we don't, although we could put that 5 on the 16 to the 5th power, that'd be a huge number to have to take the square root of. So I think it's cleaner if you do the root first because you're shrinking down the numbers. What's the square root of 16? Okay, the square root of 16 is 4. You probably still want to have your calculator here for this. What's 4 to the 5th? 4 to the 4th is 256 times another 4. Is that 1024?
1024, yeah.
Okay.
1024.
$16 to the 5/2 power is 1024.
Let me go punch that in.
As we move through this logarithm journey that we're beginning this week, we're going to see that logarithms are just a fancy way of expressing an exponent. And so these exponent problems are essential to mastery of the logarithm material that we're going to be doing. And number 11.
Now, we've been given fractional exponents. We wrote them with radicals, but look at this. Rewrite with rational exponents. So here they want you to write it with a fractional exponent. In other words, you're getting rid of the square root symbol.
This is going to be important when with the logarithms. Whenever I run into a logarithm containing a radical, my trick will be to rewrite it using an exponent. So we're really going to be going more radical to exponents rather than exponents to radicals as we work with logarithms. The square root of 17. How do I rewrite that using an exponent? We have 17. That'll be the base. Not squared. Okay, 1 over. We're going backwards from the square root of a goes back to a to the 1/2. So it's not squared, it's 1 over 2. 17 to the 1/2 power is the same thing as the square root of 17.
Write example under there and do cube root of 17.
Okay.
Suppose it had said
the cube root of 17. Oops. Suppose it said the cube root of 17. We'd have 17 to what power? What power is the same as a cube root? Okay. To the 1/3. Going backwards from the radical, a cube root is the same thing as a 1/3 exponent. 17 to the 1/3. Well said. But I didn't circle my answer. Did you type in that answer for number 11?
I don't think I did. Let me see. 17 raised to the 1/2.
1/2. Oh, I was going to type 1/3. Okay. All right, here's a good one. Number 12.
I want you to write it with a rational exponent. Remember, rational is another word for what?
Starts with an F.
Not FOIL or factor.
Maybe fraction. A rational number is any number that can be written as a fraction. A rational exponent is an exponent that can be written as a fraction.
So it's telling you your answer should have a fractional exponent.
And this is going to be one of those tricks we add to our bag of tricks when working with logarithms. We have that when you have a radical, rewrite it using an exponent. What exponent is the same thing as a 7th root? 1 over 7. There. For my final answer, 18 to the 1 over 7 power.
18, let me type that in. Oops. 18 raised to the 1 over 7.
Do any of y'all use the little key shortcuts? Tony uses the hot button for a fraction, but the key shortcut is a shift and up arrow. I find that quicker than using the hot button, but either way. Any questions?
Okay, so tell me what you do on this one. If it had been, this is another number 12. I just said similar problem, so he can show me or tell me what
18.
What would the exponent be here? What's the fraction? 1 over 5.
Shift up arrow.
Oh. Huh. Okay. I think I'll just click that.
Okay, I can't blame you. Okay.
Oh, do you want
Any questions up to this point? Okay, we've reviewed our properties of exponents. I'm ready to define what an exponential function is.
So you're actually starting the...
Generally, we don't mention when we're moving from the foundations material to the college credit material. It's all blended so that you shouldn't be able to really tell. But here I'll tell you, we're leaving the foundations material. We're about to start the college credit material. An exponential function. I'm going to define that. When you see the letter B, from here on in, as we move through the rest of the semester, wow, let's assume that the letter B is a positive number and it doesn't equal 1. An exponential function to the base B is a function in the form, am I getting too low? Okay. Y equals, or f of x equals, remember y and f of x are the same thing. Y or f of x equals b to the x, comma, where x can be any real number.
But B can't. B has to be a positive number, but not 1.
Really, what I should have just given you the condensed version, the condensed definition. What's special about exponential functions is that the variable is located in the exponent. Up until now, we've had x squared, x cubed. It was always variable to power. Now, what's different is that the variable is in the exponent. Instead of x squared, we have 2 to the x or 3 to the x. Variable is in the exponent. And the exponent may not just be a single letter x, but to be exponential, it has to contain a x. You could have, okay, I'll just make some examples of exponential expressions. I said 2 to the x, 3 to the x. As long as it's any positive number, why do we discard 1? Why do we say, oh, b can't be 1? 1 to the x power, 1 to anything will always be, doesn't matter what exponent you put on 1, you're still going to get
1. That's why they discard that possibility of 1. Because if b were 1, it would equal 1. 1 to any power is 1. But you could have like a fraction or 1/4 to the x. As long as there's an exponent, a variable in the exponent, you could have 1/3 to the 2x minus 1. The variable is in the exponent position. That's what I mean by exponential. We're going to do two things today involving two broad topics. We're going to graph exponential functions, and then we're going to start solving exponential equations. We'll start by graphing exponential functions. To graph exponential functions, we're going to do it the old-fashioned way. We're just going to make a table of values and plot points. We're going to generate ordered pairs. Remember, I said that the domain of an exponential function is any real number. So you can plug in anything you want to for x. But my advice, don't get too creative. I wouldn't go any further than, say, 2 to negative 2 using the integers. So let's look at that first one that we're graphing.
Number 13.
Graph that
fancy tool.
There's no fancy graphing tool here also. Graph the function on paper and then choose the correct graph. But I just happen to have some ancient Egyptian papyrus. Maybe I'll graph it on that papyrus.
No.
Oh, I gotta use paper.
paper.
They're not going to let me use. What if I have a tablet and a stylus? Can I use that?
No. It's got to be on paper. I just find these instructions funny.
Y equals 4 to the x. And it's possible. Now, you've never worked with exponential expressions before. I'm assuming most of y'all have not seen the expressions where the variables are in the exponent. Am I right? Yes? Okay. We're going to make a table of values. We're just plotting points.
You said generate
and I said
-2.
Use the integers from 2 to negative 2. So we'll say 2, 1, 0, negative 1, and negative 2. Now remember, you'll need to remember the properties of exponents that we've already seen. Well, for the first one, plug in that 2. I don't think there's a lot of I don't think there's the plugging in the 2 is difficult. You have a 4 squared.
Don't say 8.
4 squared is equal to. So we have the ordered pair 2, 16. We're just generating ordered pairs. Let's plug in 1 for x. We have a 4 to the first power. What's that going to give us? 4. So we just generated the ordered pair 1, 4. In a moment we'll plot these points. Here we're just on paper. You're right, on paper. Plug in 0. Be careful. What's the first thing we did today? I think we looked at the definition of 0 exponent.
Remember that
what is 4 to the 0 equal? Be careful. I'll tell you right now, don't say 0. 1. Okay. That's why we started with that today. 4 to the 0 power is defined to equal 1. So we just generated the ordered pair 0, 1. Now we're going to plug in negative 1. Be careful. Even though we've been we're working with negative exponents earlier, common mistake I see is people say negative 4. No, that's not what a negative 1 exponent is. How do you work with negative exponents? Plug in that negative 1. Down here we're going to plug in that negative 2. So you have 4 to the negative 2 power. 4 to the negative 1 power. It's an integer to a negative exponent. An integer to a negative exponent.
Second rule we stated.
It's the second rule we stated here. An integer to a negative exponent. To get rid of the negative on the exponent, you make it a 1 over, and then the exponent becomes positive. So we have 1 over 4 to the first power. Well, what's that going to give us in terms of what's 1 over 4 to the first? 4 to the first is 4, so just a 1/4.
Having seen that one, what about the next one? And I'll follow the 4 to the negative 2 is?
It's 1 over 4 to the 2. What's that going to reduce to? It'll be 1 over 16. Any questions on our logic? Notice 1/4, 1/16. Those fractions are getting smaller, but a positive number to any power will always have what sign? Our base is positive. Note, a positive number to any power will always equal what sort of a number?
Positive.
Am I going to get a negative? Will I ever get negative y values? No. A positive number to any power will always be positive. So we're never going to get any negative y values. What about 0? Will we ever get a y value of 0? Here's my scratch work. 4, is there any power we can put there to give us 0? A positive number to any power is positive. It's not going to equal 0. These things, the y values, are going to stay positive. Let's draw.
But be close to 0.
They'll be close to 0, but they're going to stay positive.
So you're drawing it on the paper the way they wanted you to.
Yes. Sometimes when you're making the little table of values, you're going to get some numbers that, oh, I don't want to plot those points. They're too far up. And here's the funny thing. The very first point, 216, here's 2. I don't want to go all the way up to 16. They'll be way up here somewhere. So I'm going to not bother with that one. I'll start with 1, 4. We go right 1, up 4. Then left, right, 0, up 1. Here's the y-intercept. That point is, this graph is going to pass through the y-axis at the ordered pair 0, 1. Now, these things have the small y values. Those are the interesting points. We're going to go left 1 and up 1/4. Here's left 1. And imagine breaking up that first little increment. There's 1. We just want to go up 1/4. What would that be? About right out there? Negative 2. Imagine breaking that interval from 0 to 1 into 16 equal little units. It's going to look like it's just sitting on top of the x-axis, isn't it? But technically there's always going to be a little bit of space between the curve and the x-axis. To the naked eye, it don't look like it's touching that x-axis. But in reality, it is.
It's just going to be flat.
We say that the x-axis is a horizontal asymptote. The graph is getting closer and closer to the x-axis, but it never really touches it. Think about if we had plugged in, let's say, a negative 10. Don't write this down.
but that would be a 1 over 4 to the positive 10. Can you get a decimal approximation for that? 1 divided by 4 to the positive 10 is a huge number. You have $1 and you're dividing it among this huge number of people. How much is everyone getting? Nothing. But that's okay. It's converting to scientific notation, so that's a point 0.00000009. To the naked eye, if you were plotting that point, it would look like it's sitting right there on the x-axis. But technically, there's always a little bit of space. Let's look and see it. Let's look at the graphs.
Oh, definitely not A. I think there's only one that I even need to blow up. Which one does it look like it is?
D, blow up D, let's see. Do it like that, pop it out. There it is.
Right, 1 up 4. And look, it looks like it's on the x-axis, doesn't it?
But in reality, there's always a little bit of difference. Nothing lies below the x-axis. If we have points down here below the x-axis, that means the y values are negative. But we've already said a positive number to any power will always be positive. So this exponential graph has nothing down there below the x-axis.
Tim, wait. This is not problem 19.
Number 19. What is it? Oh, I must have written the wrong problem number. What number is it?
13.
13. This is number 13. Okay.
Problem 19. Oh, you're really wanting to be finished fast.
No, I don't know where I got that 19.
Well, let's go to 14.
Okay. The next one. Number 14.
Y equals 2 to the negative x.
We'll make ourselves a table of values again. And we'll go 2, 1, 0, negative 1, and negative 2. We're going to plug in the 2 first. So we're going to have 2 to the negative 2. We're plugging a 2 into that x there. We have a negative in front of it, so we're evaluating 2 to the negative 2.
Don't say negative 4.
What's 2 to the negative 2 equal? A negative exponent is the same thing as, that's saying the reciprocal of 2. That's 1 over. That's 1 over 2 to the positive 2, which gives us the fraction 1/4. So we're going to go right 2 and up 1/4. Now we'll plug in 1. We're going to get 2 to the negative 1. And what's 2 to the negative 1? Okay, that's 1 over 2 to the first, which is just 1 over 2. Oh, I like this one. Plug it in 0. This one's easy, provided you know the definition of 0 exponent. That says we're going to have a 2 to the 0 is neither positive or negative. It's just a 2 to the 0, which reduces to 1. Now plug in negative 1. That negative 1, that negative sign here, the red negative, is going to combine with that black negative. What's that going to give us? A positive 1, and 2 to the positive 1 is just 2. Plug in the negative 2. We have a 2. That negative here, the red negative is going to combine with the black negative. What will my exponent actually be? A positive 2, which gives me a 4. Y'all see the ordered pairs that we generated? I should have put the table over here and written the ordered pairs out beside it. But y'all see we have a 2, 1/4. I'm going to put
2, 1.
That's what I'm going to do. 2, 1/4. Do y'all see the ordered pairs that we generated? 1. It's 1, what? 1/2. Okay. And what's the next ordered pair we generated? 0, 1 and good and okay. It's just easier looking at them like this than with all this stuff in between there, okay? We draw our XY grid. I don't know why I'm putting these little tick marks down here. Are we going to have any of the graph drawn down here below the x-axis? Will anything be drawn down here? No, because the y-coordinates are always positive. You'll go left, right, and always go up. A positive number to any power is always positive. So we go right 2 and up 1/4. Right 2, up 1/4, that's right out there. Then right 1, up 1/2. So we're just barely moving up a little bit. That's midway between 0 and 1. That looks like 1/2 to me. And then 0, 1. Negative 1, we're going up 2 units. Negative 2, we're going up 4 units. Do y'all see the pattern? It's going down. It hits at the y-intercept 0, 1. But this time you'll see when you're graphing these things, you'll expect one side to be nearly flat. You'll expect the other side to be extremely steep. And the first one, the flat side was on the left. The steep side was on the right. For instance, if you plotted 3 on that other one, it would have been right 3 up 64 units. Where would 64 be? It'd be way off the page. So realize this side is extremely steep. The other side is extremely flat.
Smooth curve, one end looks horizontal.
The other one is nearly vertical. So let's choose the correct graph. Then I want to make some generalizations about this. A, B, C, or D.
Which one does it look like? Which one should I pop out? Definitely not that one or that one. Or even that one. Is it this one?
That's what it looks like.
1, up 2, left 2, up 4. So there's a 1/2, there's a 4th, an 8, a 16th. So which one was it? It was the first one.
A.
They're not labeled A, B, C, D.
Oh,
it's the first
it's
one.
not. Oh, it is.
Right.
Okay. You should expect, when you're graphing exponential functions of this form, you should expect, switch over to my paper, one side to be extremely steep and the other side extremely horizontal.
With no negative y values.
With no negative y values, that's right. A function that's rising from left to right is illustrative of exponential growth. The thing it's real, it goes along. I guess they say the population is exponential. For years and years, the population hardly ever grew. It was that flat part, okay? And then during our lifetime, we've gone from 3 billion to 4 hours, mine and Tony's, not y'all's, but we've gone from 3 billion to 4 billion to 5 billion to 6 billion, 7 billion. We're 8 billion now, right? We're in that extremely steep part of the exponential growth. But for an exponential graph, you're expecting two possibilities. One illustrates exponential growth. The left side is flat, the right side is steep. The other side, the other possibility is exponential decay. Exponential decay, you expect the left side to be real steep and the right side to go down so that it's extremely flat. This graph is a typical graph illustrating exponential decay. Radioactive waste. It never completely disappears. Radioactive waste, it has half-lives. You wait 10,000 years, half of it is decayed. You wait another 10,000 years, another half is decayed. But it just keeps on being cut in half, but it never goes to zero. So this is an example of exponential decay. The best we could hope for with radioactive waste is that one day it'll be so little of it left that it's not harmful to life. But that's enough about that.
Mm-hmm.
Now, exponential equations.
Solving exponential equations. So we're going to solve equations where the variable is where?
It's equations where the variable is in the exponent. You can spot an exponential equation. No, wrong thing. Equation with the variable in the exponent. That's what I mean by an exponential equation. We're trying to solve equations where the variables are up in the exponent position. Now we know an equation has to have an equal sign. We know what we mean by an equation, but what makes it exponential? The variable is in the exponent. There are two generally accepted forms for solving exponential equations. The same base method and the logarithm method. We haven't seen logarithms yet, so we're not going to look at that, obviously. We'll look at the logarithm method next week. But right now, we're going to say two methods of solving I think I'm going to Roman numeral these two methods. The first one is the same base method. And I think same base.
Doing today.
That's what we're doing today. The same base method says that if you have the same base on both sides, then the exponents have to be equal. And if you think about it, I'm going to make a real basic example. Let's say 5 to the x is equal to 5 squared. What's the only thing that x could equal? For the left side to equal the right side, it should be obvious. What would x have to be? 2. If the bases are equal, then you can drop the base and set the powers equal. Now, I don't think there are any problems that are going to be set up like this, where the bases are already given to you in equal form. You're going to have to use your properties of exponents to manipulate each side so that you get the same base on both sides.
Why don't you do the example, 7 to the x equals 49.
Okay, that's a good one. I think I'll use this color here. Here's another one. 7 to the x is equal to 49. 7's a prime number. Realize the base is the thing that's being written down low. That's the thing written big. And I assume y'all know what I mean by the power of the exponent. That's the thing up high. So 7 is a prime number. You're not going to change 7. You better be able to change 49. Can we write 49 using a power of 7? How can we write 49 as 7 to a power? 7 squared. So you're going to have to be getting the same base on both sides. And once you get the same base, you drop the base. The only way the left side can equal the right side is if the powers are equal. And that's what we'll be doing the rest of this class today, the same base method. I want to mention the other possibility. This is Roman numeral number 2. This is the logarithm method that you're not going to see until next week.
You'll use that if there's no common base.
Okay, use if there is no common base. For example,
7 to the x is 25.
Well, I think you're making that a little fancier than it needs to be. 7 to the x is equal to 9. Well, 7 is a prime number. You're not going to change 7. Can we write 9 as a power of 7? 7 to the first power is what?
7 to 1.
7, here I'm thinking to myself, 7 to the first power is 7. 7 squared is? We skipped over 9. Is there a power we can put on that 7 to give us a 9? You cannot get a common base. In that event, I'll say no common base. Use logarithms. And we'll see that next week.
9 days.
Okay. Next week. So you have something to look forward to. But that means everything we're doing today, the equations we're solving today, must be set up in a way so that you can get a common base. They can't give you something like where 9, you can't write 9 as power of 7, you can't write 7 as a power of 9. For these problems, you must be able to get a common base. To illustrate,
I think 16 is what we decided.
that 16 is a better first problem.
Then
We'll
we'll
get
go
rid of
back
that calculator.
Okay,
16. You think? I don't put it down there. Okay, this is number 16. Solve the equation analytically. 2 to the 2x minus 3 is equal to 16. Notice the way the variable appears in the exponent. That's what makes this an exponential equation. The variable is up there in the exponent position. I have two bases here. I have the base 2. What's the other base? 16. You say, well, there's no power on that 16. Sure there is. If you don't see a power, you assume a power of 1. So the bases are 2 and 16. I start with the smaller base. Well, 2 is a prime number, so I'm not going to change 2. I better be able to change 16 so it's a power of 2. We have 2 to the 2x minus 3. We better be able to write 16 as 2 to a power. 2 to what power gives us a 16? 2 to the first is 2. 2 squared is 4. 2 times 2 times 2. 2 cubed is 8. What about 2 to the fourth? 2 raised to the fourth power. Sure enough, that gives me 16. You say, well, suppose that hadn't been a 16. Suppose it had been a 15. Then this method doesn't work. The problems have to be set up in a way so that you can get a common base. And before you think that that's not really as restrictive as you think it might be, okay? So that is not really, since so many in real life applications of exponential equations.
Common base.
Yeah. So once you have the same base on both sides, you drop the base, set the exponents equal. So we have drop the base 2's, the big 2, set 2x minus 3 equal to 4. The equation you get won't be that bad. Your work is going to be getting the common base on both sides. And I'll warn you right now, sometimes you may need to change the base on both sides. But once you have the same base on both sides, drop the base, set the exponents equal. There's only one sensible next step to solve this equation. Add 3. That's going to give us 2x equals 7. And then divide to give us x equals 7 over 2. For my final answer. 7 over 2. Oh. 7/2. Go back to number 15. There's a property of exponents that I think I should remind you of right now. The power rule of exponents. The power rule of exponents. Yes. This power rule is going to be used quite a bit over the next few assignments. The power rule of exponents says that if you have a base, let's say b, is raised, b to the a is raised to the n power. We have a base to a base, a power to a power, not a base to a base. We have a power to a power. If you have a power raised to a power, you multiply to write it as a single exponent, a times n.
So you're getting rid of the parentheses.
That's correct.
And you multiply the exponents to do that.
When you have a power raised to a power, you multiply the exponents. For example, if you had 2, I think I'll change it from a 2. I'm going to do a 3 squared to the, I guess I'll use a 4 power. This, I'm just trying to justify this property here, okay? That outside 4, that says you have 4 factors of 3 squared. So you have 3 squared times 3 squared times 3 squared times 3 squared. That red 4 says you have 4 factors of 3 squared. Now what does 3 squared mean? What does that little exponent 2 there mean? How many factors of 3 do we have in that one little expression? 2. That's 3 times 3, So this is 3 times 3. Another 3 squared, that's 3 times 3. Another 3 squared, that's 3 times 3. And that last 3 squared, that's 3 times 3. How many factors of 3 do we have there total? 1, 2, 3, 4, 5, 6, 7, 8. So 3 squared to the 4th power, you could have just rewritten that as 3 to the 8th power. 2 times 4 gave me an 8. Would have been cleaner if I just used an x squared to the 4th.
Yeah, but you're just trying to justify why we're multiplying there. Hopefully that's clear.
Okay, looking at number 15. Okay. We have 25 to the x is equal to 5. 25 to the x power is equal to 5. Let's switch to my paper. What are my two bases? 25 and 5. I'm going to start with the smaller one. 5. Well, 5 is a prime number. You're not going to change 5. It can only be written as a 5. Well, I don't see an exponent there. So we assume it's a 5 to the 1st power. Now 25. Can we write 25 as a power of 5? That x there is written there. I'm about to write 25. How can I write 25 as a power of 5? 5 squared. And look at that. We have a power raised to a power. What are we going to do with that 2 and x? 5. We know the exponent over here is a 1. What exponent do we have on the right-hand side? On the left-hand side? Power raised to power, so you multiply 2 times x gives me a 2x. Any questions on my logic there? This is the work. It's this thought process, getting that common base on both sides. Any questions? Because once you do that, once you get the same base on both sides, and when I say the same base on both sides, I mean without any parentheses. Okay, once we had that power to power, we had to get rid of that before we were able to drop the base, drop the 5s, set 2x equal to 1. What's that about to give me for x? 1/2. For a final answer of x equals 1/2. Any questions there? Take a moment and look at that. I always go to the smaller base and ask myself, can I use that? Can I write the big base as a power of the smaller base? And yes, we were able to. 25 we wrote as 5 squared. We had a power raised to power, so we multiplied the powers. At that point, we had the same base on both sides. Drop the base, set the exponents equal, and solve. Any questions there? Number 17. Okay, 3 to the 2x minus 7 is equal to 9. Okay, suggestion for a common base. What do y'all think we're going to use? I think 9 is the big one. I think we're going to have to use 3. We're going to change that 9. How can we change the 9 using a base of 3? Okay. Haley was thinking, what side are we going to change? That's what she was saying the 9 about. She didn't understand the question I was asking. I was asking, what are we going to use as the base, the smaller number 3? And once you do this, it's almost it's almost finished. What do I do now? Is he going to write any more big 3's down? No, we have the same base on both sides, so we drop the base, set the exponents equal. Now, isolate the x. There's only one sensible next step. What is it? Plus 7, so that's going to give me a 2x equals 2 plus 7 gives me a 9, and then divide by 2 to give me x equals 9 over 2. 9 slash 2. Number 20. Let's jump down and do 20. Don't worry, we're going to go back to the other ones in a moment. We're not just forgetting about them. 16 to the 3x minus 6 is equal to 64 to the x plus 3. 16 to the 3x minus 6 is equal to 64 to the x plus 3. Tony, you better pull out that calculator of yours. I'm going to do this. Look what I'm going to do. I have to close it or reopen it. Okay. What are my two bases? 16 and 64. My thought process, I start with the smaller one. Can I use 16 to rewrite 64? 16, I'm asking myself, here's my thought process. 16 to what power gives me a 64? 16 to the first power is what? 16. 16 squared is 256, isn't it? We just skipped over 64. 16 to the first power is 16. 16 squared is 256. We don't have an integer that we can put on 16 to give us 64. My point is, sometimes you have to change the base on both sides. Just using 16 isn't good enough. Okay, well, how can we write 16 as an exponent? Using exponents. What to what power gives us 16? I'm thinking of one thing right off. 4 squared is 16. 4 squared is 16. Hey, but can we use 4 for 64? 4 to what power gives us 64? 4 to what? Can we write 64 as a power of 4? I couldn't hear you. Cube, I agree. So we can change both of them. We're going to change both sides to 4s. 4 and 4. Y'all said for 16 it's 4 squared. For 64 it's 4 cubed. Don't forget the other exponents, 3x minus 6 and... Okay. This is probably one of the messier problems when it comes to exponential equations. It's not probably, it is. Okay. We can't drop the 4's yet. We need 4 to the power equals 4 to the power. Then we can drop the 4's. But as long as we have those exponents there, we're stuck. What do you do when you have a power raised to a power? You multiply. A power raised to a power, you multiply. What are you going to do when you take 2 times 3x minus 6? We're going to have to distribute. So multiply by 2, multiply by 2. 2 times 3x gives me a 6x minus 2 times 6 gave me the 12. What am I going to have here? We're going to have to distribute again to give me 3x. 3 times x is 3x plus 9. 3 times 3 is 9. Any questions there up to this point? Because at this point, we're now ready to drop the base and set the exponents equal. As I said, the real work in the problem is getting to this point where you have the same base on both sides, so you can drop those 4's and set 6x minus 12 equal to 3x plus 9. Let's get all the x terms on the left side. What do we need to do to get the x terms combined over here? Oh, well, okay, so you want to move, add 12? Okay. Add the 12. What are we going to do about the x's? Minus 3x. Minus 3x. It does. 6x minus 3x just gives me a 3x equals, what have we got over here? 21 divided by 3. I wasn't expecting a nice integer as an answer, but it did. X equals 7. Yeah, any questions there? Question? Go see what he said. Is Joseph back here? Okay. Wait, hold on a minute. Okay. Sometimes you have to change the base on both sides You have to change the base on both sides sometimes. A common mistake, I think, is for people to use 16 to the 4th power, because 16 times 4 gives you 64. That's a common mistake. If this were a multiple choice question, that wrong answer, one of the distractors would be what you got if you use 16 and 16 to the 4th. But 16 to the 4th is way bigger than 64. So, did I punch that number in? Yes. Oh, okay. So now you want to, let's see. An irrational number. I need to write a little bit. An irrational number is a non-repeating, non-terminating decimal number. It is a non-repeating, it doesn't repeat the same block of digits over and over, like 0.3333 or 0.121212. It's non-repeating, but it's also non-terminating. The decimal values never end. Non-repeating, non-terminating decimal number. A rational number can be written as a fraction, one integer over another integer. Irrational numbers cannot be written just as integer over integer, but their decimal values never end.
So we need a way of expressing the value of an irrational number. Probably the most famous example of an irrational number is the ratio of the circumference of a circle to its diameter. Take the circumference divided by diameter. What is that irrational number associated with circles? Maybe pi 3.14 blah blah blah. That's an example of an irrational number. But we've been working with irrational numbers since the very first day. Any square root that's not a perfect square is an irrational number. So like the square root of 2, the square root of 3, that's why we have to write them like that. Because that's the only way to express their exact value, because the decimals just keep common and common forever. The square root of 4, no, that's a perfect square. The square root of 5, any square root that's not a perfect square is an irrational number. Well, there's an irrational number that has important applications in business and scientific applications. It's called the natural exponential. And we denote that number with the lowercase letter e. An approximation which you don't need, okay? But I'm going to go ahead and write out an approximation. Just like pi is approximately 3.14, the natural exponential is approximately 2.718. But those digits just keep common forever, pretty much, randomly. So the natural exponential, if you see a lowercase letter e, that's not a variable. That is a number. And since it's irrational, you can't write e as a power of anything other than e. So if your equation has a base of e on one side, you better have a base of e on the other side. So with that in mind, number, where is it? 18.
Yeah.
We skipped over some problems, and that's why we skipped over them, because I wanted to do the ones that didn't involve e's. Okay. Look at that. This is number, what number is it? 18?
18.
Once you accept that the letter e is representing a number, then these things are pretty easy, because you know what the base has to be. E to the 7x minus 1 is equal to e to the 5th power, all raised to the x power.
Well, if there's an e in it, that's the common
E
base.
has to be the common base. If you have an e on one side and you're going to get a common base, you better have an e on the other side. Because if you don't, then you're going to have to use logarithms, and we haven't gotten there yet. So e is my common base. I need it to say e to the power equals e to the power. I have to do something here before I can drop the e. What is it? The power raised to a power. So that is e equals e. That's a 7x minus 1. Power raised to power, we multiply to give us a base, exponent of 5x. I agree. And then we can drop the bases, set the powers equal. So you have 7x minus 1 is equal to 5x. I think we should move the 5x to the left and move that constant term to the right. I think that would be, there are fewer negatives in that way, going about it like that. So, what should I do? Add 1, so that's going to give us we'll have a positive 1 on the left side. What are we going to, no, on the right side, what are we going to have on the left side? Minus the 5x. Anthony and I were mirror twins. That's the rarest form of identical twins. They're like a mirror. Mm-hmm. Okay, and I was supposed to be left-handed, but of course they were not having any of those left-handed people in Nacogdoches, Texas. No way. They only had to tie my hand down one day in first grade, learning to write, and they discovered
This was before kindergarten.
This was back then. You didn't do kindergarten. Okay, you didn't have to go to kindergarten. Okay, but they did. They tied my
had kindergarten back in the 60s.
We did not start school until 70.
We would have been in kindergarten in the 60s.
Wow, that makes us sound old. Yeah. Old as the hill. So, but every now and then I still confuse my lefts and rights, and I think it goes back to the fact that I was supposed to be left-handed, but instead, what did they do? They taught me to write with my right hand, and despite that,
normal.
Yes, I was going to be normal, as they put it. But of course, and I should mention, I won all those penmanship awards despite having to use the hand that was not my dominant hand. So, but anyway. So what I'm saying, getting lefts and rights, I'm getting lefts and rights confused today. You didn't put in the answer?
Wait a minute. Look at this. Number 18. This doesn't happen often, but it has to happen. Let me just, what was that answer? 1/2?
Mm-hmm. Oh, look at that. 18 and 19 were the same question.
And there. Okay. Now.
Okay.
Let's do this.
Number 19. What percent of the nation's population is left-handed? What is it, 10%? Is that it? That's the number I hear. But if you look at the percent of American U.S. presidents that have been left-handed, it's huge. Over half of the U.S. presidents are left-handed. Do you all know that? And so there's something about left-handed people rising to power. We have any left-handed people in here?
I'm sure
if so,
we do.
I'm sure, yeah. Okay, you're going to rise to power. You're going to rise to power. And don't forget the little people that you met along the way like us, okay? Oh, you can forget everyone else. Just don't forget us, okay? I'm going to be like, that was my student. There's only one. Here, all right. I'm not going to change the left side. What am I going to do over here? Yeah. What am I going to do on the right side? 11 times x. And then drop the e's, set the exponent equal.
Well, heck, I think it's still going to get the same answer.
It is, isn't it? Do a minus 11x, and a plus 1. I don't know why I'm choosing to show that. In the past, we've just been doing it in our head, but today
there's so much going on.
Maybe that's it. Oh, look at that. This one is also x equals 1/2, isn't it? They don't all turn out to be 1/2, okay? It's just a coincidence.
Hannah, are you looking at your number 19? Did yours turn out to be 1/2? Yes?
Yes.
Oh, okay. Maybe
was it the same
numbers
numbers or were they different numbers? They were different, but well, I guess that programmer had fun. He was like, I'm going to make sure every answer for this problem turns out to be 1/2, and I'll see if my boss catches it. The boss mustn't have called it.
Okay, well,
what about number 20?
We've already done 20. See? Oh, wait, there's 20.
And
now
21.
Maybe go back to
number 21.
Put the 1 over in red. He's going to rewrite, when he writes this problem, he's putting the 1 over in red to try to give y'all a hint of what we're going to
how we're going to set this up.
To be.
If there's e's in the problem, then e has to be the common base.
Also, I don't like a base that's a fraction. E to the 6 to the, is that x plus 4?
We had some
1 over e to the negative x is equal to 1 over e to the 6th to the x plus 4. Okay.
Did we have some problems earlier where we had a 1 over and we had to write it with a negative exponent?
If you're going to use the common base method to solve an exponential equation containing an e, you better have e's on both sides. And e is going to have to be the common base. So I know I'm going to need an e there. I'm going to need an e there. We need to rewrite 1 over e to the 6 as just e to a power. Let's go back. What were we doing a while back?
Number 4, no, 5, 6. Look at number 6.
There. 1 over p to the 9. Remember we said that's p to the negative 9. 1 over 7 to the 9, 7 to negative 9. We're going to have to rewrite. Let's do this one first. 1 over e to the 6. How do I rewrite that without the 1 over? It's going to be e to the negative 6. Now, I don't even see an exponent on this. I'm going to give you a hint. If you don't see an exponent, there's an assumed 1. So what am I going to have here? E to the negative 1. Take a moment and look at that. Any questions? Because once you realize you can do that, then it starts to, the problem itself starts to look better. We have powers raised to powers. What are we going to do when we have powers raised to powers? Negative 1 times negative x is going to give me what? A positive 1x. Negative 1 times negative x gives me a positive 1x. Oh no, I smeared my ink. Can y'all tell what that is? That's saying negative 6. E to the negative 6 to the x plus 4. What are we going to do with the negative 6 and the x plus 4? To give us negative 6x, I agree, minus 24. And now what can we do? Drop the e's, set the exponents equal. I think I'd get the x's collected on the left side by doing what? Plus 6x, 1x, plus 6x is giving me 7x equals a negative 24. And then divide by 7 to give me x equals negative 24 sevenths.
Negative 24 over 7. Let me write that. Negative 24 over 7.
Look back at my work a moment. I don't like a base to be, when I'm solving an exponential equation, I don't like a base to be a fraction. So, if the base is a fraction, the bases are fractions, I use negative exponents to rewrite it. And then we had powers raised to powers, so we multiply. And after that multiplication, we had the same base on both sides, drop the base, set the exponents equal, and solve.
To get rid of a 1 over, make the exponent negative. Get rid of a 1 over, make the exponent negative. Now,
Okay.
last two
The last
problems.
two, number 22. Write this down. Number 22.
That's not distributed fraction. Remember, you multiply both sides.
Let's see. The square root of 3 to the, what is that, x plus 6 is equal to 27 to the, just x, Earlier I made the remark that when we're working with logarithms and I run into a radical, a trick that I have in my bag of tricks is to rewrite that radical as an exponent. That's exactly what we're going to do here.
Go back to my little page where I get the first page.
Right there, right here. That square root of 3, the square root of 3 is the same thing as an exponent of 1/2. So I have 3. That square root is an exponent of 1/2 to the x plus 6 is equal to, okay, the base on the left side is a 3. 3 is a prime number. You cannot change that 3. Which means if we're going to get a common base, what had we better be able to use over here? A 3? Okay, how do we write 27 as a power of 3?
Let's see.
How do we write 27 as a power of 3? We have to be able to do that or else this method fails. 3 to the first is 3. 3 squared is 9. 3 cubed is, there it is, 3 cubed is 27. We now have powers raised to powers. What are we going to do?
Oh, okay. You do. Okay.
So what do y'all say we're going to have to do? Distribute. You take the 1/2 times the x plus 6. 1/2 times x, that's just 1/2 x, plus, we're distributing, we're multiplying the 1/2 times x, the 1/2 times 6. What's 1/2 times 6? 3. Over here we have a power raised to a power. 3 times x is 3x. Any questions on our logic up to this point? Now, you drop the bases, set the exponents equal. You have 1/2 x plus 3 is equal to 3x. I'd multiply through and get rid of the fraction first. What could I multiply through by to eliminate that fraction? A positive 2, the only denominator is a 2. That means the least common denominator is a 2. How many terms do we have to multiply by 2? 3. We have 2 terms on the left, 1 on the right. So I agree, we're going to multiply through. We have to multiply 3 times. We're multiplying by 2. 2 times 1/2. What happens there? The 2's cancel, so you just have a 1x plus here. 2 times 3, that's a plus 6. Here, 6x. Any questions on our logic right there? This is one of those times I think I'd get the x's on the right side by doing what? Minus x to give me 6 equals 6x minus 1x is 5x, and then divide by 5 to give us x equals 6 over 5 for my final answer. Any questions? This one's the most involved equation so far, in my opinion. You have to remember how to write radicals as rational exponents, use the power rule of exponents. You even get to solve an equation containing a fraction within this one problem. Are we ready to do the last one? Okay. This is number, do you think I have room down here? I'll write small. This is number 23. It's another square root of 3. It's square root of 3 to the x plus 8. The square root of 3 to the, I don't think I'm going to have room down there. It's number 23. The square root of 3 to the x plus 8 is equal to 81 to the x. Square root of 3 to the x plus 8 is equal to 81 to the x. Okay. What do y'all think I'll do first? There's really only one correct first step. Okay, get rid of the square root. The square root of 3 is the same thing as the exponent. One half. The square root of 3 is the same thing as 3 to the 1/2. 3 is a prime number. You cannot change 3. That means you better be able to write 81 as 3 to a power. 3 to what power gives you 81? 3 to the 4th power, correct?
3 to the 4th would be like 9 times 9, right?
Now what are we going to do? Distribute, okay, power raised to a power. Power raised to a power, we distribute. 1/2 times x is 1/2 x, okay, plus 1/2 times 8, 4, over here, 4x, 4 times x gives me 4x, and then what can we do? Drop the 3's, set the exponents equal, so we have 1/2 x plus 4 is equal to 4x. I like to get rid of the fraction. I think there's fewer chances for you to mess up by getting rid of the fraction. If we're going to do that, we'll multiply through by 2.
Seems vaguely familiar.
Is it the same thing?
No, it's very similar though.
Okay, distributing the 2. What are we going to get here? Just 2, the 2's cancel, so you have a 1x plus here. Two times 4 is 8 equals here 8x And I'd combine the x terms on the right. Minus 1x, yeah, minus 1x. So we have 8 equals 7x. And then divide by 7 will give me x equals 8 over 7.
This idea of taking square roots and writing them as a 1/2 exponent is going to be critical
when we start expanding and condensing logarithms.
Okay.
And we're going to start that on Wednesday.
Yeah.
Logarithms
will be spread out over 2 days.
And then we have another section of solving exponential and logarithmic equations. The exponential equation, we already know how to solve exponential equations. One method is that second method. Suppose you can't get, where is it? Remember, I Roman numeraled it because I thought it was important. Here it is. What we're doing today is the same base method. But next week, suppose it's impossible to get a common base. If it's impossible to get a common base, that's the logarithm method. And we'll see that next week.
Are there any questions?
This is the last haul. This is the last leg of the semester, in my opinion. Once we make it through the logarithm discussion, well, we still have matrices and Kramer's rule and stuff, but still, this is.
I'm about to stop the recording. Any questions?